tough lecture. Monday it will be even more tough. So, but we start doing real calculations. So today is lecture number 3, and we discuss magnetism of non-interacting fermions. Magnetism of Fermi gas. And as we learned on Wednesday, as long as we are relying on paradigm of Fermi liquid, almost everything what I'm going to say about magnetism of ideal Fermi gas will equally be applicable to magnetism of Fermi liquid. Okay, and we start with the paramagnetism, Pauli paramagnetism. The goal of today's lecture is to show you that magnetism is intrinsically quantum phenomenon. So there is no classical analogy of the magnetism, and we will see that by discussing two topics today, namely Pauli paramagnetism and Landau diamagnetism, that both sort of magnetisms associated either with spin degree of freedom or with orbital degrees of freedom are really quantum, because there is no classical counterpart to the spin quantum number, as well as the orbital motion, as we will see in quantum case, is quantized, and therefore the diamagnetism will be related to quantization of the energy levels. So, but let's start with a simple thing. As I have already mentioned, fermions, particles, elementary particles, as well as quasi-particles, which are characterized by spin. Moreover, the theorem, Pauli theorem, tells us that the spin of fermions is half integer. So we are discussing simplest possible case excitations in ideal Fermi gas. So we are talking about electrons and holes, and spin of these excitations is 1/2. So we are discussing 1/2. The magnetic moment associated with the spin quantum number mu is equal to Bohr magneton times S divided by value of spin, and Bohr magneton contains h bar, is modulus E h bar over 2 mc. This is Bohr magneton. And in previous lectures we discussed that the ground state of the electron gas is the Fermi sphere, so the surface is Fermi sphere, and we discussed the ground state of the Fermi gas in the absence of magnetic field, and therefore all states in the Fermi sphere were degenerate with respect to the spin projection. I remind you what you're supposed to know from quantum mechanics. In order to characterize spin, we actually use Pauli matrices, and we construct Pauli matrices. One of them is supposed to be diagonal, such a way that we select the quantization axis. Typically, the quantization axis is selected along the magnetic field. So please don't ask me. Every year, students ask me where the z-axis is directed, and moreover, what is the direction of magnetic field. It's ill-posed question because it's our choice to direct the axis, and this is other way around. We select the direction of our coordinate axis based on some physical arguments like existence of magnetic field. So if we assume that there is a magnetic field in the problem, we select the quantization axis, and the Z Pauli matrix is diagonal, and it accounts for two projections of a spin up and down with eigenvalues 1 and -1. So the simplest possible Hamiltonian, which accounts for interaction between magnetic moment associated with spin and magnetic field, is Zeeman Hamiltonian. This is a scalar product of magnetic moment to magnetic and magnetic field. And since we assume that the quantization axis is along magnetic field, so magnetic field now is along B direction. So sometimes people write it in the way, so B is now parallel to Z, or Z parallel B. We can write it, you see that here I divide it by the value of spin, which is 1/2. Sometimes people incorporate it in the G factor, so this is G mu bor B and sigma Z. So this is what we have for magnetic field, right? And also factor 1/2, and the geomagnetic ratio in this notation is equal to 2 for free electron. We discussed this geomagnetic ratio and lambda factor for the situation, which is lambda factor, actually, for the situation when you have a spin-orbit interaction in the last part of our lecture course, when we discuss the magnetism of strongly interacting electron system. I assume that you discussed in the course of advanced quantum mechanics how to sum up spin and orbital degrees of freedom and what is the lambda factor. Okay? Did you?
Yeah, spin orbit, yes. Yes.
Okay, so what then happens with the Fermi sphere and with the states in the presence of magnetic field? So we create a imbalance between the number of electrons with a spin up and electrons with a spin down, because the magnetic field selects a direction. So in the absence of magnetic field, if I write down parabolic dispersion, the number of spin up and spin down was the same. Now, in the presence of magnetic field, I have more electrons with a spin up than spin down, and as a result, there is a magnetization in the system which is going to be proportional to the value of magnetic field. And the first exercise, warm-up exercise, which we are going to do now, is to compute this magnetization. And as I said, paramagnetism here means that you apply magnetic field and the system becomes magnetized. You remove magnetic field and the system goes back to demagnetized state. In a sense, if we plot magnetization as a function of magnetic field, we will see that for small enough magnetic field, it's linearly proportional, and the coefficient, the proportionality coefficient between the magnetization and applied magnetic field, this is a response function, which is the susceptibility. So this is what we are going to compute. So, as I said, there is no interaction in the fermionic system. Let me write down the energy of the electrons when spin up and spin down. So, and as usual, I will count the energy from the Fermi energy. And let's for the moment consider temperature equal to 0. Case, the ground state, then we discuss temperature correction. So with spin up P square minus m. So I subtract the Fermi energy. This is the chemical potential at 0 temperature. I don't want to use mu for chemical potential now because it might be confusing. We denote mu magnetic moment. So this is why I'm saying I'm at 0 temperature and explicitly write that this is Fermi energy. So we are dealing with this state. We have this sign minus. So it is minus mu Bohr times B. Again, minus mu Bohr because geomagnetic ratio times 1/2 is equal to 1. So this is minus because we have minus here and this eigenvalue is 1. The energy of electrons with spin down is P square over 2m minus Fermi energy and plus mu Bohr. And of course, the chemical potential is long-term right chemical potential. This is the same. Otherwise, the system will be unstable. If there is a drop of chemical potential or imbalance of chemical potential, the system is mechanically unstable. However, what I would like to do now, I would like to denote this quantity, namely this one, as the Fermi energy with spin up, and this one as a Fermi energy with a spin down. Okay, so on Wednesday we introduced the concept of the density of states, and there is very important reason to do it. So we said that density of states nu over epsilon is the number of states in the interval of energies, and by the definition this is 2 times integral over dp over 2 pi h cube delta epsilon minus epsilon p. Writing the phase volume with power 3, I again assume that I'm dealing with a 3-dimensional situation. So, and one of the reasons to do it, suppose we need to compute some thermodynamic quantities which contain summation over all states over p, some function over p. So what we do, we multiply this summation by the integral, which is equal to epsilon minus epsilon p. So what I did, I multiplied by something which is equal to 1, and now I will take sum over p, replace it by the integration, and take this, which is the density of states. So my integral will then be integral over the energy, density of states of energy, and then some function of energy. So this is a reason to simplify calculations introducing the density of states. Okay? One of the reasons. And what we did, we compute the density of states for 3-dimensional electron gas characterized by parabolic dispersion law. I think in the course of solid state physics, or maybe in the course with Professor Nersisian, you also computed density of states for tight binding model. If you didn't do that, please do it. Did you discuss what Van Hoff singularities are? Okay, yes. Then you know. So, let's compute number of electrons with a spin up per unit volume. So, based on this equation, this is 1/2, and 1/2 because I defined the density of states for spinful case, explicitly assuming summation over 2-spin projection. Therefore, with this definition of density of states per spin projection, I need to write the factor 1/2. So this will be integral from 0 to infinity over energy density of states over energy, and the Fermi distribution function over energy. So if I assume temperature equal to zero limit, the Fermi distribution function is step function, correct? So what we have 1/2 integral from 0 to the Fermi energy up, because as I said, magnetic field lifts out the degeneracy, and Fermi surface for spin up is different from the Fermi surface from the spin down, and I have d energy times mu epsilon. The same way, number of electrons with spin down per unit volume is 1/2 integral from 0 to Fermi energy down. I already assume that temperature equal to 0 here, and I have d energy nu over epsilon. Okay? The magnetization is extensive quantity. If I write mu, which is going to be mu bar n up minus n down, and I said magnetic field is polarizing system such a way that it creates imbalance. So magnetization, which is mu per unit volume, is equal to Bohr magneton n up per unit volume minus n down per unit volume. So I plug in what I have already derived. So this is a mu Bohr, and here I have integral. This is integral from, well, 1/2 integral from 0 to Fermi energy up minus the same integral from 0 to Fermi energy down. So what I have is the integral from Fermi energy down to Fermi energy up dE nu. This is my magnetization, correct? And now let's recall, and this are Fermi energy up and Fermi energy down. Let me rewrite it explicitly: 1/2 Bohr magneton integral from Fermi energy minus Bohr magneton times B to Fermi energy plus Bohr magneton B, where the Fermi energy denotes the Fermi energy in the absence of magnetic field. And what we did on Wednesday, when we computed the density of states, it has a square root behavior, and so this is a new energy, and Fermi energy is somewhere here. So what we are going to do now is to approximate this integral, and there is a good reason to do that. So let me argue that we are in the situation that Fermi energy down and Fermi energy up form very narrow stripe around the value of undisturbed Fermi energy. So in order to do it, let's come to the numbers. As I said, the typical Fermi energy of the metals, and we are discussing paramagnetic metals, is of the order of 1 to 10 electron volts, which is from 10 to the 4 to 10 to the 5 Kelvin. How big is it compared to magnetic field? Again, we can use a conversion of units, and in order to do it, we need to write the energy from one side as a Boltzmann constant times the temperature. This is conversion energy into units of temperature, and then we need to write down the energy as a function of magnetic field, which contains Bohr magneton times magnetic field. So when we use this conversion, we can convert the values of magnetic field into the units of temperature. And if you do that for, they say, the system with a G factor of the order of 1, we can say that 1 Tesla, which is unit of magnetic field, is approximately 1 Kelvin. This is what you will get. So this is for G factor equal to 2. For G factor much smaller, you will have a bit different conversion. And what we are saying that this deviation from the undisturbed Fermi energy is for realistic magnetic field, and many laboratories have strong magnetic field, and 10 Tesla is already strong magnetic field. With a constant magnet in lab, one can probably reach fields like 40-50 Tesla, which several labs, few labs in the world have. If you want to have a field higher than 100 Tesla, you can do it only in a pulse for very short, say, millisecond time interval. For higher fields, you need to do something else, because you can estimate how big currents should be in the coil in order to produce such huge magnetic field. So what I'm saying that in everyday life situation, we do deal with magnetic fields of the order of 1 Tesla, which is approximately 1 Kelvin, which means this is 4-5 orders of magnitude smaller compared to the Fermi energy. Okay, if it is so, I'm integrating on very narrow stripe, and what I can do, I can write down approximately, this is 1/2 Bohr magneton. I will multiply it on the value of the density of states at this point. So I will approximate it by flat density of states times the difference on the upper and down limit, which is 2 Bohr magneton B. And as a result, what I obtained, that magnetization of the electron gas is equal to mu Bohr square times density of states at the Fermi energy times magnetic field B, value of magnetic field B. I remind you that the value of density of states at the Fermi level is equal to MPF divided by pi square h cube. Okay, this is a nice equation which confirms what I said, that for small magnetic field we can use linear response, and magnetization is proportional to the value of magnetic field. Now it's very straightforward to compute susceptibility. Susceptibility, as I said, is proportionality coefficient. If we define the linear susceptibility, we can write it down that this is magnetization divided by magnetic field for small magnetic field. If we define differential susceptibility, this is dm over dB in the limit b goes to 0. And you see, as long as we are in a linear response regime, these two definitions coincide, and susceptibility chi is equal to mu Bohr square times density of states at the Fermi level. Which is the constant? So the first message which we learn is that paramagnetic susceptibility, and paramagnetic means that we apply magnetic field and we create imbalance between electrons up and down, is linear. If we increase field further, it will become non-linear, but in reality there are some hysteresis properties, so the system has a memory. So just to emphasize, we are dealing with this region. So we'll come to discussion of hysteresis a bit later. Okay, so far so good. The last comment is what happens if we have a finite temperature. If we have a finite temperature, unfortunately I erase it, we have a Fermi distribution function. So instead of computing integrals with a step function, we need to proceed with computing integrals with a real Fermi distribution function. If you didn't do it in the course of statistical mechanics, Jean-Paul will tell you in a tutorial while computing specific heat how to deal with the temperature dependence integrals with a Fermi distribution function. And to cut a long story short, if we write this as a Pauli susceptibility at zero temperature, the susceptibility at finite temperature will be equal to Pauli susceptibility at zero temperature times 1 minus some temperature dependent correction. And as you know from the course of statistical physics, and I also mentioned it last time, all temperature corrections are scaled as a temperature over Fermi energy. Since we are in a Fermi liquid regime, it should be temperature over Fermi energy square. So what we have here is pi square T square over 12 Fermi energy square. And again, for realistic temperatures of the order of room temperature, this is 10 to the power minus 6 correction. So with a high accuracy, we can say that even for room temperature, the susceptibility of non-interacting Fermi gas is constant. Okay? Questions? So this was easy calculation. Let's now start doing a bit more involved calculations. If no questions, I will switch a gear and discuss the susceptibility of the electron gas associated with orbital degree of freedom. And in order to do it, I'm afraid I need to repeat with you what is quantum oscillator and how motion of the non-interacting electrons in magnetic field is related to one-dimensional quantum oscillator. Okay? So repetition is not bad. If you feel that you know it by heart, and you don't need it, then I probably ask one of you to come to the blackboard and proceed with calculation for the quantum harmonic oscillator. If not, I will do it in a quick way myself. Okay. So the chapter number 2 is Landau diamagnetism. So the cartoon which we are going to keep in mind now is that we apply a magnetic field, electron semi-classically will move on semi-classical trajectory. Let me adopt this language with a spiral type semi-classical trajectory. And what I'm going to do now is to disentangle completely spin and orbital degree of freedom, which is true if spin-orbit interaction is small. So what I did before, I considered the spin part of Hamiltonian, which is Zeeman part, minus magnetic moment times magnetic field. Now, let me forget that electron has spin and concentrate only on orbital degrees of freedom. I can do it because the Hamiltonian consists of two parts, and in principle I can take into account both, but it is additive. And for additive quantities, I can consider each of contributions separately. So what I'm saying is that my Hamiltonian now will be p squared over 2m. Just kinetic energy, nothing else, because I'm considering non-interacting electrons. So what is p? We remember that by introducing magnetic field, we need to replace small p, which is minus I h nabla, by, I would probably at some moment use units h equal to 1, to long derivative, which is minus I nabla minus e over c vector potential. So, and the operator nabla applied to the vector potential produce U magnetic field. This is how the vector potential and magnetic field are connected. Sometimes people use curl, so one can write notation curl A is equal to B, or rot A is equal to B. Both have this meaning, so if you allow me, I will proceed with these notations. Okay? And the first thing which we need to do is to recall what are the energies of how the energies are quantized and how do we come to the picture of Landau levels. In order to do that, we need to solve the stationary Schrodinger equation. Nothing depends on time. I'm solving equation H psi is equal to E psi. To do that, of course, I'm dealing with gauge invariant quantities. Let me adopt some particular gauge based on this equation. Namely, I will assume that the vector potential has a form 0, x dot b, and 0. Let's check that this shape of vector potential indeed consistent with this equation. Okay? So, nabla times A, it's a differential operator, is a vector. This is ort Ex, Ey, Ez. This is d over dx, d over dy, d over dz. And this is 0, x dot b, 0. So this is the determinant of nabla A. So then this is Ex times this determinant, d over dy 0, minus d over dz, this is 0, plus Ey times determinant d over dx 0, d over dz 0, which is 0, plus Ez times this, d over dx x times b, which is b, minus 0. So this is indeed b. Okay. But this gauge, well, I can use another gauge, read it in the book. The theory is gauge invariant, therefore fixing gauge is not a big deal. But you may also check that with this gauge, the scalar product number of A, nabla of A, which is divergence A, which is d over dx Ax, plus d over dy Ay, plus d over dz Az, is equal to 0. This is also important because then P and A are commuting in this situation. Okay? While P and X do not. You remember that we are dealing with quantum mechanics and the operator of the momentum and displacement are non-commuting operators. So let me write down the Schrodinger equation for three-dimensional case. We consider three-dimensional motion of an electron subject to magnetic field. So this is minus 1 over 2m d2 over dx square plus minus I nabla minus E C x dot b. This is py square over 2m minus d2 over dz square times psi, which depends x, y, z, is equal to E times psi x, y, z. Okay? So, first of all, this is z direction, and this is how magnetic field is rotated, is directed. So, first of all, I see that semi-classically the electron moves along z direction freely. Therefore, I can write down that psi x, y, z is equal to I p z z. So this is actually d over dy. Sorry. What I have here, and I can also see, since this commuting quantity, that I can look for the wave function also as a product I p y y times the wave function which depends on x only. Okay? Well, when I choose different gauge, for example, I can write it as y times bx. I will then replace x by y. So this is the form of the wave function which I am using, and I'm going to plug into the Schrodinger equation. And since now the function depends on only one variable, I will replace the partial derivative by full derivative over x. So this is minus 1 over 2m d2 over dx square plus py minus e over c b times x square over 2m plus pz square over 2m psi x is equal to e times psi x. So I reduced my Schrodinger equation, which is a partial differential equation with three partial derivatives with respect to x, y, and z, to ordinary second order linear differential equation, reducing the problem to one-dimensional motion. So let me rewrite this equation as d2 over dx squared psi x plus energy minus m omega L square x minus x naught square over 2 psi x is equal to 0, where E is energy minus pz square over 2m. X naught is a shifting of the centrum of the orbit. X naught is Cpy over EB, and m omega L square should be equal to 1 over m EB over C square. Therefore, Larmor frequency omega Larmor is EB over MC. Okay, so in 2 minutes what I did, I started with description of orbital, three-dimensional orbital motion of an electron, and I arrived at certain differential equation which describes quantum harmonic oscillator. I think if you did not do that on your lectures of advanced quantum mechanics, you nevertheless should be familiar with this problem, which is one-dimensional quantum harmonic oscillator, which is a particle in parabolic potential, right? Okay, so what do we know about one-dimensional oscillator? We know that the energies in parabolic potential are quantized, so E should be equal to h omega L n plus 1, right? Therefore, the energy of my electron E, which is pz square over 2m plus h omega Larmor n plus 1. However, So again, to have a picture in mind, let me plot parabolic potential, and then we have, so this is u over x, this is x, and I took the system, so x naught is equal to 0. So we have, for harmonic potential, we have equidistant levels, and moreover, we have so-called zero-point motion. The ground state corresponds to the energy h omega half. So this is a zero-point motion of harmonic oscillator. And these levels, quantized levels, are called Landau levels. Okay? Let's recall and compare these states of harmonic oscillator with a state in a box. So what we not have a harmonic potential, quadratic potential, and if we take a box with a coordinate Lx, Ly, Lz, then the energy of this particle in a box with the Lx, Ly, Lz energy should be Pz square over 2m plus Px square over 2m plus Py square over 2m, because we don't have interaction. If we compare this energy, and let me put in this box, with this energy, we see that Px and Py degrees of freedom actually translated to the levels of harmonic oscillator, which means that we started with a dense comp of the levels in the box, which depends on 3 quantum number, and somehow we collapse levels into Landau levels. These are Landau levels, this one. Which means that these Landau levels are highly degenerate. And in order to understand and quantify the level of degeneracy of Landau levels, the next step which we are going to perform is to compute the density of states for the problem in a magnetic field. So the logics of remaining part of the lecture is as follows. I will spend some time in computing density of states, and then I will proceed with the computation of thermodynamic potential omega in the presence of magnetic field, assuming that, of course, magnetic field is much smaller compared to Fermi energy. The thermodynamic potential omega is a function of magnetic field, contains magnetic field independent term, and this is what I ask you to compute at home. This will give you equation of states, plus there will be some magnetic field correction, which in accordance with the Fermi liquid, Fermi gas rules, will be proportional to magnetic field square. The magnetization is a derivative of thermodynamic potential with respect to magnetic field with a sign minus. So I will compute magnetization associated with the orbital motion. So the electron moves, electron charged particle, he moves semi-classically along the orbit. By moving, charged particle produce some response, some magnetic field which is going to compensate your magnetic field. So we compute magnetization and we compute susceptibility, and this will be the end of the story. But and then we compare the paramagnetic susceptibility, which I have already computed in very simple and straightforward calculation, with the diamagnetic response, which I'm going to compute now. Okay. Any questions so far about logics or whatever? So let's then discuss the degeneracy. In order to do it, let me first say that the orbit is inside the box. So the centrum of orbit, namely x naught, should be inside the box. Okay, if I write it this way, then CPy over EB should be inside the box, which means that Py is between 0 and EBLX divided by C. So this is a condition of a Py. Again, I can restore H bar everywhere, and I will probably do it at the end of the lecture, but for the moment, although I keep H bar here, I will not keep it everywhere, so maybe it's even better for consistency to remove H bar everywhere from very beginning. So H bar is equal to 1. So what we need to calculate at the end of the day is the number of states with a momentum from PZ to PZ plus dPz. So we need to compute this number of states. Okay? So this D and Z is Lz times dPz over 2 pi. Again, H bar will be sitting here. The same time D and Y is Ly times dPy over 2 pi. However, nothing depends on Py and Px in our model. So what I need to do, I need to integrate. So in order to find Ly, I need to compute the integral from 0 to Py, this one, d and y, which is Ly over 2 pi, then I have Lx, and then I have Eb over C, and that's it. So the n, which accounts for degeneracy, is then d and z times ny, which is Lx times Ly times Lz divided by 2 pi square times Eb over C dP. And since I did everything correctly, what I have here, Lx times Ly times Lz, is the volume of your box, right? So are you with me? Do you understand what I'm doing? Because the rest, I will divide dN by dE. And I use a connection between energy and Pz, and I'm done with calculation of the density of states. So I don't compute integrals. However, I compute explicitly dN over dz, taking into account the huge degeneracy of Landau levels. So now I need to add factor of 2 associated with spin, and I will write down that dN over dE is 2 times volume divided by 2 pi square EB over C dPz over d energy. From this equation, Pz is equal to plus minus square root over 2 times m E minus omega L n plus 1/2. Therefore, I have two branches of Pz. I can write it as d modulus Pz over the energy. However, since I took only one branch and there are two, I need to multiply it by yet another factor of 2. So this is 2 times 2. This is 4 times volume divided by 2 pi square EB over C. So by replacing Pz by its modulus, absolute value, I accounted for extra factor of 2. So then the rest is straightforward. dPz modulus Pz over dE, so this is 4 times volume divided by 2 pi square EB over C, and I have 1 over 2 square roots 2m E minus omega L n plus 1/2 and 2m here. Let me see that I didn't make any mistake. And this is the density of states. So contrast to what we saw before, where the density of states has just square root monotonous behavior as a function of energy, here we see that the density of states has a square root singularity as soon as your Landau level crosses the Fermi energy. So if we fulfill the condition that denominator is equal to 0, so we change it. As soon as the energy coincides with this for particular number of your Landau level, you have a 1 over square root divergence of your density of states. Good. So I will use this density of states to compute the thermodynamic potential. We will see that for superconducting ground state, the density of states will also have a 1 over square root singularities at the values of energy coinciding with the values of gap of your superconductor. Yeah. Before I proceed with the calculation of omega, so this is what I'm going to do. Omega is minus t, sum over all quantum states, logarithm 1 plus e to the power mu minus epsilon e over temperature. Let me discuss the difference between classical and quantum case. In classical case, we elongate our momentum replacing p by p minus e over c vector potential, which means that in the calculation of this integral, what we do have a continuous integration over 3 momentums, px, py, and pz. And since this is a continuous integration, we can shift the variable of integration, introducing new one, namely px minus e over c ax, and so on and so forth. And by shifting the variables of integration, you eliminate completely vector potential, means magnetic field, from computing of your thermodynamic potential. Which means with this simple transformation, you make your thermodynamic potential magnetic field independent, and therefore there will be no effect associated with it whatsoever in classical limit. In a quantum limit, we see that this integral actually contains summation over projection pz and also summation over n associated with the quantization of your Landau levels, which then form highly degenerate states, and therefore mu minus energy, which depends on Pz and n over temperature. Therefore, we cannot shift the variable in this summation anymore, and we will get a response proportional to magnetic field square, which is associated with quantization of level. Therefore, the diamagnetism which I'm discussing with you now is again intrinsically quantum phenomena associated with the quantization of levels in parabolic potential. And parabolic potential appears due to magnetic field which is introduced in the problem. Okay? So, again, I will introduce the density of states. So I will delta epsilon minus E P n d epsilon. So summation over Pz gives me the density of states which I have already derived. So as a result, I will write down that omega, and again Kb is equal to 1, is equal to minus T integral over the energy sum over n Landau levels density. Let me write it this way. 4 times V divided by 2 pi square E B over C m divided by square root over 2m epsilon minus omega L n plus 1/2. This is the density of states, and then I have a logarithm 1 plus e to the power mu minus e over temperature. From 0. Okay? So this is the object I'm going to evaluate, and therefore I can erase this one. I hope I did not make any mistake. What I see in this square root, that in order to have argument of square root being positive, my summation should be from minimum value. So there is minimum value n, well, no, it's maximum value. So summation over n is limited from above. So maximum value of n maximum is equal to epsilon divided by so epsilon minus omega L half divided by omega L. So this is epsilon divided by omega L minus 1. So this is the maximum n, which guarantees me that the argument of a square root is positive. On the other hand, okay, that's first comment. So I have integral and summation over n, and there is a function, so energy is contained here and there. And I would like to evaluate this integral by parts. I have integral u dv, which is then equal to uv minus integral v du. So I use u as logarithm 1 plus e to the power mu minus e over temperature. And dV is 1 over square root. 1 over square root. So V will be the integral of 1 over square root, which is square root. So therefore, I write it this way, minus 4 times V temperature divided by 2 pi square EB over C. This is what we have as d modulus Pz over d energy. So in this sense, dV is dPz. And V is therefore modulus Pz, which is square root over 2m energy minus omega L n plus 1/2. Okay? So I have summation over n. I have square root over 2m energy minus omega L n plus 1/2 times logarithm 1 plus e to the power mu minus epsilon over t in the limit, and actually the limit is equally, I can write this integral from epsilon minimum. Epsilon minimum is found from the same condition that the argument is positively defined, and maximum is translated to epsilon minimum, which is actually omega L n plus 1/2. So you see, and here it's from epsilon minimum to infinity. So this is the first part. And then I have V du, so this is minus integral, so V is square root over 2m epsilon minus omega L n plus 1/2. So this is summation over n is taken here from 0 to infinity, and now I need to compute du, and du is the derivative of logarithm with respect to the energy. So this is 1 over 1 plus e to the power mu minus epsilon over temperature times derivative of exponent, which is mu minus epsilon over temperature, and times derivative of the argument of exponent with respect to energy. This is minus 1 over temperature. Okay? So, this is how I integrated everything by part. Let's now look at the first term. At energy equal to minimum energy, the argument of the square root is equal to 0. And we have some logarithm, we don't care, because logarithm is multiplied by 0. At energy equal to infinity, this exponent is equal to 0. We have a logarithm of 1. We multiply something by logarithm is equal to 1, and therefore we'll get 0. So this term is irrelevant. It is 0, both in the lower limit and upper limit. And what remains is this term. So what do we see here? So this is the Fermi distribution function, right? And from this moment, we can assume that temperature is much smaller compared to the Fermi energy, and therefore we can approximately replace the Fermi distribution function by the step function. Besides, temperature cancels out here and there. We are fine to take 0 temperature limit, and what remains, minus and minus gives me plus, and there is a minus in front. So therefore, the thermodynamic potential omega is equal to minus 4 times volume divided by 2 pi square times EB over C. Temperature is cancelled out. So this is sum over n, integral from 0 to Fermi energy. And it's square root over 2m E minus omega L n plus 1. DNG. So what I will do, it's very easy to integrate over energy. I have simple integral square root. I will do that, and what remains is summation over n, and I will perform this summation using some approximation. Also replacing it by integral, because there are many Landau levels. Quantization, the distance between levels is Larmor frequency, and Larmor frequency is proportional to magnetic field, and we know that magnetic field is small compared to the Fermi energy. So it's huge number of Landau levels. We're not dealing with quantum Hall effect, where it's physics of ultra quantum limit of very few Landau levels. Here we assume that there is a huge number of Landau levels. So let me first integrate over energy. So this is minus 4 times V over 2 pi square EB over C, and I have sum over n. So the integral over energy will give me 2m energy minus omega L n plus 1/2 to the power 3/2. This is from minimum energy to the Fermi energy. And there is a coefficient 2/3, of course. And there is 1 over square root over 2m. If I'm not mistaken. No. Now, let me do it this way. I will write square root over 2m here, and therefore there will be square root over 2m here. And I will delete 2m. Yeah, now it's correct. Well, previously it was also correct, but I would prefer to write it that way. First of all, at minimum, it is equal to 0, because minimum energy is precisely the energy coinciding with Landau level n. So what I have is integral on the upper limit is minus 4 times volume divided by 2 pi square EB over C times square root over 2m, and I have a summation from n equal to 0 to n maximum, and here it's a Fermi energy minus omega L n plus 1/2 to the power 3/2, and I have 2/3. Okay? So this is what I do have. What I need to do is to perform this summation. Without proof, let me introduce you to Poisson formula and Poisson summation. Well, the very easiest and simple way is to say that we have very dense system of Landau levels. As I said, they are separated by Larmor frequency, and of course I can replace summation by integration. This is the first step, is correct, but this is not sufficient, because I would like to take into account magnetic field dependence of this sum, which is encoded in Larmor frequency. This is EB over MC. So I need to take into account this dependence, and therefore I need to be more precise than just replacement of the summation by the integral. So Poisson summation says that if we have a sum over n, some function from 0 to a node, some function over n, so then what we can do, we can write it as the integral from -1/2 to a node plus 1/2 fn dn. This would be corresponding to transformation from discrete variable to continuous variable, but we also need to add this remaining so-called Cauchy-Maclaurin term, which is 1/24. And here it's f prime n node plus 1/2 minus f prime minus 1/2. I'm not going to ask you for proof of this system. You can take in the literature, and there is a rigorous way to show that this approximation works quite well, as long as we keep only first term in Taylor expansion. Okay? So, what is our function Fn? This is Fermi energy minus omega L n plus 1/2 to the power 3/2. What is F prime with respect to n? F prime is 3/2. By the way, let me also adopt notation omega L n plus 1/2 is EB over MC times n plus 1/2. I can divide by 2 and multiply by 2. So what is here? H bar is equal to 1. This is a Bohr magneton. So this is Bohr magneton times B, 2n plus 1. So this is identical. This and this is identical, and since I expressed my Pauli susceptibility for paramagnetic response in terms of Bohr magneton, I would probably from now on keep using Bohr magneton notation. So this is Fermi energy minus mu Bohr B 2n plus 1 to the power 1/2 times the derivative with respect to n minus 2 mu b b. Right? Now n node, the maximum, which is n max, is given by 0 of the square root. So this is Fermi energy divided by Larmor frequency minus 1/2. So, which means that n node plus 1/2 is just Fermi energy divided by Larmor frequency. Larmor frequency is proportional to magnetic field. This is a huge number, 10 to the power 5, 6, 7, depending on the value of magnetic field. So F prime at n node plus 1/2, we need to plug in the n node plus 1/2 there, which will give us 0, right? because this is a condition of nullifying the argument. So f prime at minus 1/2. If a node is equal to minus 1/2, what we have is just Fermi energy. This is 3/2 Fermi energy to the power 1/2 times minus 2 mu bar B. So we know what this is, and what remains is to compute the integral from minus 1/2 to a node plus 1/2, Fermi energy plus minus 2 mu bar B 2n plus 1 to the power 3/2 dn is equal to 2/5 Fermi energy minus mu bar B 2n plus 1 to the power 5/2. And I need to divide minus 1 over 2 mu bar B, and I need to take limits from minus 1/2 to n node plus 1/2. In the upper limit, it is 0. In the lower limit, it gives me minus and minus give me plus 1 over 2 mu bar B times 2/5. And I have Fermi energy to the power 5 over 2. Good. So let me combine everything together. And what we can immediately realize, you see that this is factor in front. The first term contains magnetic field in denominator, which perfectly cancels out with magnetic field in numerator. So what I'm saying is that omega is equal to some omega node, which doesn't depend on magnetic field. And this term is precisely what I asked you to calculate for free electron gas. Because if it doesn't depend on magnetic field, this is the same as per magnetic field or without, doesn't matter. This is what will give you equation of states. In a sense, I already derived this equation of states with a proper coefficient. I'm not going to trace this term anymore because I'm about to take some derivatives, and what I'm going to concentrate in this term. So this is minus 1 over 24 times minus f prime. So which means I have minus 4v divided by 2 pi square EB over C times square root over 2m times 1 over 24, this coefficient with a sign plus, and f prime over minus 1/2 is equal to minus 3/2 Fermi energy to the power 1/2 times 2 mu bar B. That's it. So if I did things correctly, and I did, so what we get, we have minus, and all together we have a plus, and we have magnetic field here and there, we have magnetic field squared. Okay? This is what we were fighting for all the time. Let me now slow down a little bit and write down all coefficients correctly. So omega is equal to omega node plus I think I forgot to third, which is coming from here. Plus. Let me write it 1/3 because I have 8 divided by 8 times 3 divided by 24. So this is this one. I write it 1/3 1/3 volume over 2 pi square EB square over C square root over 2m Fermi energy. I have EH over, I will delete 2mc. This is Bohr magneton. So that's it. I can write it as omega naught, and you may follow me. 1/6 Bohr magneton square, density of states at the Fermi level, which is MPF over pi square times volume times B square. What is important that the sign is plus, and since I did everything correctly, you can check the coefficients. This is what you get. So now everything is easy. Magnetization is minus d omega over dB. The first term is independent of magnetic field, so this is minus 1/3 Bohr magneton square density of states at the Fermi level times B. And susceptibility is dm over dB. Let me concentrate on differential susceptibility. It doesn't matter, we are in linear response. Or this is minus d2 omega over dB square. This is minus 1/3 mu Bohr square times density of states at the Fermi level. So what we obtain is that diamagnetic response gives us negative susceptibility, which is understandable. So electron, as I said, moves along the semi-classical orbit, and it produces magnetic field which is directed in the opposite direction in order to compensate magnetic field. And the susceptibility, diamagnetic susceptibility, is negative and also constant. I will write the paramagnetic susceptibility, which is Pauli, which we obtain, which is mu Bohr square density of states at the Fermi level. Let's now discuss something. The result which I obtain looks a bit strange. Namely, I am saying that the orbital motion and spin behavior are two additive quantities. Therefore, I can consider them separately, and what I need to do at the end of the day, I need to take these two response functions, sum them up, and get the final results. If I do so, I will see that the sum of diamagnetic and paramagnetic susceptibility is always positive. Because 1 minus 1/3 is equal to 2/3, which actually means that diamagnetic metals are absent in the nature. This is kind of silly conclusion which I can derive based on this calculation. So what is wrong? Because we know that there are some metals which are neither ferromagnets or antiferromagnets, like iron is ferromagnet, for example. Copper is non-magnetic. It doesn't. It cannot be magnetized even if you cool it down until very low temperature, and it repels out the magnetic field, which means it's diamagnetic. So what is wrong? And the wrong thing is the following. Actually, I have Bohr magneton here and Bohr magneton there, but in principle, this Bohr magneton contains different masses because the orbital motion fills the environment. So the electron moves in a certain environment, which means it is dressed by the effect of this environment, and the magneton Bohr in para is related to the inverse bare mass of the electron as elementary particle, while Bohr magneton dia is inversely proportional to the effective mass. Therefore, chi para divided by chi dia modulus, this is 1/3, and I have m star over m node squared. Which means that if your effective mass associated with your environment is, for example, sufficiently larger compared to the bare mass of electron, you can compensate this factor 1/3, and then it resolves the paradox that there are no diamagnetic metals. There are, because the masses, as I said, are different, entering the different susceptibilities. This is one comment. And the second comment is just suggestion for you to read something yourself. In principle, I may equally tell this story considering independently, considering simultaneously the orbital and spin motion. And if I do that, what I see in my energy, let me forget about the motion along the direction of magnetic field. I may write down that energy is h omega r more, and for orbit 2 we have n plus 1/2. Therefore, if I write corresponding Hamiltonian, I can replace n by the number of bosons h omega l a dagger a plus 1/2. This is a Hamiltonian, right? Second quantized Hamiltonian. But spin degrees of freedom actually is related to the also Larmor frequency. This is Zeeman splitting. And I can write it as n fermions minus 1/2. Because n fermions has value 0 and 1. If n fermions is 1, I have plus 1/2. This is the upper part of Zeeman splitting. If I have n equal to 0, this is minus 1/2. So I can equally write it plus h omega Larmor f dagger f minus 1/2. So let me replace A by B, because B is boson, F is fermion. So if I collect these two quantities, I will get omega Larmor B dagger B plus F dagger F. So where this is operator associated with number of bosons, and this is operator associated with number of fermions. So you see that my Hamiltonian has very beautiful form, because number of fermions and bosons comes on the equal footing. And this is called supersymmetry, because Hamiltonian is supersymmetric with respect to creation and annihilation operators of fermions and bosons, which means I can rotate in the supersymmetric space. And what I'm saying is that the motion of electron spin 1/2 characterized by geomagnetic ratio G equal to 2 is described by supersymmetric Hamiltonian. And what I would like to encourage you is to read about supersymmetric Witten quantum mechanics. It's a very simple thing. It's some of when I teach quantum mechanics, actually I use this as one of example of modern, so to say, quantum mechanics. The nice thing about supersymmetric models is that you can actually simplify your Hamiltonian using supersymmetry property, and you can construct the ground state as excited state, like, let me say it in very literal way, taking square root of your Schrodinger equation. You can make your Schrodinger equation not the second order linear differential equation, but first order differential equation. You rely on non-degeneracy of the ground state, and then you construct, using Clade operator, all excited states of the model in very simple fashion. What you can see here is that bosons are characterized by positive, so to say, 0-point motion plus 1/2. This is the level lives above the bottom of your parabolic potential, but fermions, in a sense, has a negative 0-point motion, which exactly compensates each other. So the beauty of supersymmetry here, that I have the same coefficient in front of this and that. In principle, in what I said here, that the Bohr magneton is different for orbital and spin degrees of freedom, it's not always true. It's only true if the Bayer and effective mass are the same, then the model is supersymmetric. So if you're excited, read about this. There are many books. You can find it in Google. And this is yet another way to describe system quantum mechanically. My goal was to deal with statistical physics derivations, so I decided to put the comment about supersymmetry just at the end of my lecture. Okay? Any questions?
Can you please re-summarize the paradox that you solved?
Yeah. Summarizing paradox. I proceed with two independent calculations for paramagnetic and diamagnetic susceptibility. It was done by assumption that the Bohr magneton, which contains the mass, is the same for paramagnetic and diamagnetic response. By assuming that, and under that condition, I computed susceptibility. I found that the paramagnetic susceptibility comes with a +1 coefficient times mu Bohr square density of states at the Fermi level, while diamagnetic susceptibility is negative and comes with a coefficient -1/3. And therefore, the total susceptibility under assumption of equal masses, chi total, would be chi para plus chi dia, which is equal to +2/3 chi para. That whatever orbital motion you have for your electrons, the total susceptibility will anyway be positive at the end of the day. Therefore, the total response of the electron system characterized by orbital and spin degrees of freedom onto magnetic field is always paramagnetic. This is a paradox, because the nature says this is not true, and there are diamagnetic methods. When we discuss the superconductivity, we will see that superconductor is ideal diamagnet. Its susceptibility in dimensional units is -1/4π. Therefore, it cannot contain magnetic field inside superconductors. It's called Meissner effect. So what is wrong in this conclusion, which I did, which is a contradiction with observations and with what nature tells us? The resolution of this paradox is that the mass contained in the coefficient for diamagnetic and paramagnetic susceptibility are different. While the mass contained in paramagnetic susceptibility responds to magnetic field coupled to spin degrees of freedom is bare mass of electron as elementary particle, while the mass associated with diamagnetic response is different because electron moves in some crystal environment and the effect of interaction strongly renormalizes it. And therefore, the correct formula says that the ratio of para and diamagnetic susceptibility is inversely proportional to ratio of the mass square, and therefore, if the effective mass associated with orbital motion is larger than effective mass of electron as elementary particle, due to effects of interaction that can be as large as smaller, we can, at the end of the day, come to the situation where the diamagnetic response prevails, and therefore it is stronger than paramagnetic one, and this is how we can explain in very simple hand-waving argument existence of diamagnetic metals in the nature. Okay?
Yes.
So the plan is as follows. Monday we finish with the fermionic system by discussing the dielectric response of fermionic system interacting by means of Coulomb interaction. On Wednesday we start with bosons and we proceed along the very same lines. Ideal Bose-gas phenomena of Bose-Einstein condensation, then non-ideal Bose-gas nonlinear Schrodinger equation, Gross-Pitayevsky equation, and excitations and lifetime of excitations, and then we discuss superfluidity. But after 2 bosonic lectures about bosons, I think we will insert one tutorial which will help you to compute integrals with Fermi and Bose functions and also explain missing part of the specific heat, how to proceed with thermodynamics and equation of states, and also how to proceed with the computation of dielectric function with all details, because I will not be able to compute your polarization loop in full details. It's like 1 hour slow calculation. I don't have time for that, but I will sketch you it with as many details as I can afford. Any questions? Was it clear? Do you follow my logics? If you are lost, it doesn't make sense to go ahead. It's rather better to slow down. But I think the calculations which I did were not too complicated. You can follow even with the coefficient.
There was one calculation for the previous lecture on the where we had Dirac, where we had the automatic.
1 over tau. Try to think about it. Maybe I will ask Jean-Paul to repeat it again, how to estimate the inverse lifetime of the quasi-particle.
Yes.
Okay. So then till Monday. I need to stop it.